Welcome back. Today we're going to continue with arrays. Remember that we are online, so if you have any questions, you can post them to Piazza or to YouTube. We left off last time by talking about a little bit about memory management, that if you create a dynamic array, you eventually have to clean up after yourselves. And you're going to witness this in your lab this week, where if you don't clean up after yourselves, you're going to have what's called a memory leak. If you just keep grabbing memory and hoarding it, making it unavailable for your program, unavailable for other programs, eventually performance will degrade to a point where it halts, right? So remember to be good stewards of the resources that you are allocating. And to do that, once you're done with the memory, then you need to free it up by calling the free function here. And the tool that you're going to use in your lab this week is called valgrind. So what I've done is I've set up an experiment here. We've got n is equal to 1,000 here. So what we're going to do is we're going to go into a for loop here for 1,000 times. In each for loop, what we're going to do is we're going to grab 1,000 times 4 bytes of data. Why 4 bytes? Remember, that's how many bytes an integer takes. So 1,000 integers is going to be about 4,000 bytes. Not that big of a deal, right? 4,000 bytes is less than 4K. But 1,000 times 1,000 is 4 million bytes. We're not doing anything with it. This is just a toy example. But we're also not freeing it up. So we're hoarding this memory. We're hoarding we're hoarding exactly 4 million bytes of data. And when I compile this and run it, you can see that nothing really happens because 4 million bytes of data, less than 4 megs, is not that big of a deal. But when I run it through a tool like what's called valgrind, let me go ahead and run it through valgrind here, a.out. I'll end up getting a report. We'll wait for this to execute. And we've got memory leaks here. Here's a leak summary. We definitely lost 4 million bytes, exactly as I predicted. 1,000 iterations of that for loop, 1,000 integers each iteration, times 4 bytes each, is 4 million bytes lost. Now, we're not losing that memory as in like that memory is permanently deleted or anything. When the program is done executing, the operating system will reclaim all the resources that you had. But while that program is running, we're leaking memory, and that memory is not available to our program. It's not available to other programs either. Valgrind is what's called a dynamic analysis tool. Remember that we briefly talked about static analysis tools in the context of using GCC as a linter. A static analysis tool will look at your code and look for potential problems before you compile it. You forgot an ampersand there. Or printf accepts 3 arguments. You have 3 placeholders, but only 2 actual values that you're printing. There's probably something wrong there, right? Whenever you use the WALL flag, the wall flag, you're using GCC as a static analysis tool. You're analyzing your code before it compiles. Here, this is a dynamic analysis tool. It is analyzing your program as it runs, after it's compiled, as it's running. And it does that by simply adding some overhead to monitor your program to see exactly what's going on there. And so a dynamic analysis tool like this can be used for a lot of things. What's going on with my program? Why is my program running so slow? Am I leaking memory? Right? Where's my program spending the most amount of time? So that I can look to that function and try to optimize that function to make it run faster. And you'll see this in your lab this Tuesday, tomorrow. You'll run this on your own memory leak program and then fix the memory leak. You fix the memory leak by making sure that once you are done with it, you free it up. And here I'm just passing in the pointer that I was given. And so let's go ahead and execute this again on valgrind. And we'll see now that I'm freeing it up, there were no errors, and so it's not going to actually report anything. That we didn't leak any memory at all now. Okay? All right. So again, to free it up once you're done, then you use the free function. However, you've got to be careful. You must make sure you are done with the memory before giving it back, or before freeing it. Right? Once freed, the memory is no longer yours. Now, technically, it could still belong to your program, but the process of freeing it up could zero out everything, right? It could have taken that memory and given it to another program. It could have taken that memory and reallocated it to your own program. Attempts to access something that has already been freed are undefined behavior. In this particular example, it would probably work if we really tried it, but in general, it's not going to work, right? Not only that, but attempting to free something twice results in a double free error. All right? So what I mean by that is, let's go back over here and let's free it up twice. So I asked for the memory, I got my memory, I did something with it, as per this comment here, and then I gave it up. I gave it back. Can I give it back a second time? Right? I already gave it back. It no longer belongs to me. You can't give something back if it doesn't belong to you. Right? So what is going to end up hopefully happening here is I won't run it through valgrind. I'll just run it directly. But when I run it, I see a double free or corruption, right? And it aborted the program. If you run it through valgrind, it probably will output something very similar. 1,000 errors from one context. Why? Because I double freed it 1,000 times. So it monitored that entire thing and it said, you were doing that every single loop here. So 1,000 errors here. Don't do that. Right? That will lead to a double free error. Right? Being good stewards of your memory and making sure that you're doing all your bookkeeping are what we refer to as memory management. Now that gets into a couple of concepts here. Who owns memory? All right. So if you allocate memory inside a function, does the function own the memory or not? Right? In other words, whatever piece of code owns the memory, it is responsible for also cleaning it up. So we need to establish this ownership. So if I'm inside of a function and I create an array of 1,000 integers, suppose that I create it for temporary use. I'm only going to create this array and then I'm going to do some operations, but at the end of the function, I'm done with it. I don't return it. I'm done with it. I own it. Therefore, I am responsible for cleaning it up. Right? If a function only allocates memory for temporary use and does not return it, right? And we'll talk about returning memory here in a second. It is responsible. Right? It owns it and it must free it. Right? If, on the other hand, inside of a function, you create memory, or you create a chunk of an array or something like that, and then you give it back to the calling function. Because the calling function called this function expecting you to build this array for it. And then you give it back. Does it belong to you? You gave it back to the function. Don't free it. Right? So if the function returns the array, the calling function owns it. So now to understand that, let's go ahead and look at a couple of examples here. All right? And this will also get us some practice using arrays and functions. So I'm going to go ahead and get rid of all this stuff right here. Right? So let's go ahead and create one function that sums the values inside of an array. Right? So I'm going to go ahead and create that now. So we'll call it sum elements in an array or something if you want to get fancy. Okay? So let's think about the inputs for this thing first of all. All right. So I'm going to give you an array. You're the function now. You're the sum function. I'm going to give you an array, and I want you to add everything up and tell me how many things are in that array. For example, we could say that the array is primes. Right. We were playing with this last week, right? 2, 3, 5, 7, 11, 13, and 17. That's good enough, right? All right, so 1, 2, 3, 4, 5, 6, 7 primes there. Okay, the first 7 primes. I want to add those up, and I want to determine what they add up to. So what should I take as input here? What types? Should I just take one, oops, should I just take one integer? No, it's an array, right? So what should I take? A pointer, right? That's what an array is. This one down here is a static array, but let me go ahead and change the code to use a dynamic array here. Actually, I'm not going to be able to do that easily and use the prime example because then I'd have to say 2, 3, 5, etc. So I'm just going to go ahead and leave it like this. Right? But this is taking an array. A regular old integer, that's just one element. Right? This is a pointer to an element. Now remember that a pointer can point to one thing, or it can point to many things, the beginning of many things. Right? We saw this in the Python visualization tool last week. Let's go ahead and create int array is equal to malloc, int star malloc. Let's just go ahead and create an array of size 10, right? Of int. There we go. I'm going to go ahead and put this into another variable here so that we can keep track of it. And then I'll go through a for loop and set each element for int I equals 1, or 0, sorry, I is less than n, I plus plus. Remember that this is the idiomatic for loop that always, just from the context, it's going to iterate over an array of size n, right? And we'll set each value to be, I don't know, I plus 1 times 10. What values are those going to be? I goes from 0 to 9. So if I add 1 to I, that's going to go from 1 to 10. And if I multiply by 10, it's going to be 10, 20, 30, 40. Right? So let's see this in action again. Hopefully it doesn't take too long. But the creation of that pointer, right? I'll go ahead and go through this line by line. The creation of that pointer is going to end up pointing to an array of size 10 things. It's just simply pointing to the beginning of the array. That's how pointers work. They point to either one element, or they point to one element with a bunch of them behind it, right? And so we're going to use the exact same syntax here when we use it in the context of a function. And you can see here that when we iterate through this, it's going to be 10, 20, 30, 40, 50, 60, etc. Right? So let's go ahead. I'm actually going to I'm going to use this one instead of the primes. Right? There we go. So that it's absolutely apparent that we are passing in a pointer. All right, what else do we need? Anything? We can come back. Oh, yeah, go ahead.
In case you want the error codes, you could put a pointer there for the actual answer of some.
Okay, I could do a pass by reference and use error handling instead. I don't want to get that far into it because I want to stick with arrays for now. But we'll come back to this in case we need something else. Let's try to sum these up. I'll go ahead and create another variable here called sum. Is it a good practice to have variables and functions that are named the same? You're going to lose the forest for the trees there. So let's go ahead and call this something else. Call it total. Right? Okay. For int I equals 0, I is less than n, I plus plus, an idiomatic for loop, right? That iterates over the elements in an array and adds to the total. Total plus equals array sub I. Couple of problems already though. Do you see an n here? Not in the context of this function. N is, again, it's an idiomatic for loop. What is n supposed to stand for? The size of the array, the number of elements in the array, right? So, back up here, how do I determine that? How do I determine that there are 10 elements in that array, or 50 elements in that array? I have to tell the function how, right? That's part of memory management. If you pass an array to a function, you also have to tell it how many elements are in that array. Right? There is no reliable way that given an array, you can determine how big it is. That's part of memory management. That's part of bookkeeping. If you always have to keep track of how big of an array you allocated in another variable, and usually we call that variable n. Right? And then you would add documentation here to do document. Right? Okay. And now what's my return type going to be? I haven't returned anything. I should. Return what? Total. So it's going to be an integer type. All right? There's one more problem here. And again, it goes all the way back to the beginning of the semester. I do callbacks as many times as I can. What value does total have as of line 9? Who knows? Garbage. Dead beef. 0 maybe? Only if we explicitly assign it. Garbage plus 10. Garbage plus 20. It's still garbage. Always initialize your variables. Okay? So I've created this array. I've populated it with 10, 20, 30, all the way up to 100. Let's go ahead and call this sum function to get the total. Int total is equal to sum. By the way, is there a problem with me naming this variable total and this variable total? Nope. They're in different functions. Right? They're in different scopes. So it's perfectly fine to have total right here. I will pass in my array, and I will also pass in the size of that array. Now, is that correct? Array is a pointer. Star pointer takes a pointer and turns it into a regular old variable. In this case, what's the regular old variable being stored at the very beginning? Oh, I lost my visualization. At the very beginning of this? 10. Is that what I want? Nope. Okay. Is that what I want? Ampersand takes a regular old variable and turns it into a pointer. I've already got a pointer here, right? So array is what you want. Okay? And then you can print it out if you want to. Printf total is equal to %d end line total. There we go. Let's go ahead and compile this and see that it works. I won't go through valgrind. Right? 550. Right? That's 55 times 10. That's exactly what we expect. Okay. All right. That's how you give it to. Now let's get into that stewardship that we were talking about again. Who owns the memory here? Does sum own the memory? Nope. I mean, it's done with it, right? It totaled everything up. I'm done with it. Free up the array. All right. What does that do to the array down here? What if I wanted to print the elements in the array now? All right. I'll print the total, and then I'll go back and actually print the elements. Printf %d and the line array sub I. There we go. I have a feeling that unfortunately this may work, but let's go ahead and find out. There we go. Oh, did it work? Total 550. What was in the array again? Let's visualize it. 10, 20, 30, 40, 50. Is that what you got now? 0, 0, negative 79, blah, 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 blah. 22, 0, 3, 3, and then 50, 60, 70, all the way up to 100. What did we do? We corrupted our own memory because we freed it up even though we didn't own it. Right? This function doesn't own it. Who owns it? Main. So if you're going to free it up, then go ahead and do it down here. Now this is such a simple program that I would generally not do this because you're done with it. You're done with the program at that point. There's no point in freeing it up. But this is a good idea in general once you're done with it, right? So this is proper, but not necessary in the main. Right? I'll just put that down there. Okay. So this is how you use functions and arrays together. Now, that's as input. If I have an array, I give it to a function so that it can do something with it. What about the opposite? What about creating a function that returns an array? Right? So for example, get ones array. There we go. So let me go ahead and describe this really quick. This function creates a new dynamic array of the given size filled with ones. Right? So in other words, if I want an array of size 5, I want 1, 1, 1, 1, 1. I want 5 ones in there. Right? So let's go ahead and write this function, and then we'll worry about stewardship and how to call it and things like that. Right? So first of all, what should the input here be? Should I be giving it an array? No, it creates an array. Right? What should I be giving it, though? Yeah. The size, the length. Right? So again, idiomatic variable names here, n. Right? the given size and put that in the documentation, size n, filled with ones. Okay? What should the return value be here be? What? The array. And so how do I express an array? Is it just one integer? Nope, it's many integers. So what do I do? Star. Right? And you can put a space here if you really want to. I don't bother. Right? In fact, you could do it with no spaces whatsoever if you really wanted to. That's getting kind of icky though. At least one space to make it a little bit readable. 2 spaces if you like. Okay? White space doesn't matter. So help me out here. Let's write this array. First of all, what do I need? I need well, I should do, like you pointed out earlier, I should do some basic error checking, right? If n is, what would be an invalid size here? Negative values, right? If it's less than 0. You might think that 0 is an invalid value too. Oh, okay, but you can have an empty array, right? That's perfectly fine too. You just can't put anything in it, right? Yeah.
A number larger than the int maximum.
Oh, okay. You can't detect that because if it's a value that's larger than 2.147 billion, you've already overflowed back down to negative values, in which case this is what we're doing right here. Right? So what's a good flag value that I could return to indicate an error code, at least given this design? Could I return 1, an error code positive 1? What am I doing there? I'm returning a memory address 1. That may not even exist. Certainly doesn't belong to us. What is a red flag value that I could give to say that no, that was invalid? No. That's the only thing that you can do deal with pointers and have an assurance that that's pointing to nothing. Okay. All right. We did our due diligence. We did our error checking. Now let's go ahead and create that array. So create the array of the given size. How do I do that? Well, we've seen several examples already. I'll just cut and paste. All right, there's the array. How big should it be? N, and times the number of bytes that an integer takes. And this will return array right here. Okay. Now, are we done? What is in that array as of line 25? Just like total, nothing, random values, dead beef, right? Even if we're lucky and they're all zeros, that's not what we're writing. It's not get the zeros array, it's get the ones array. So for int I equals 0, again, an idiomatic for loop here. I is less than n, I plus plus. Array sub I is equal to 1. Okay? Now let's go ahead and see how we can use this now. Array is equal to get ones array. There we go. Let me go ahead and get rid of this for a second here. Okay, and I'll reuse the same n here, and then I will go ahead and print these out. There we go. Just to make sure that it actually works. Okay. Let's go ahead and compile it. Everything's fine. There. And I assure you that there are 10 ones there, right? Remember that we go 10, 20, 30, up to 100. That's the first array that we created, and we summed up, and it was 550. This is the second array that we created, 1 through 1, 10 times. Right? Let me run this through valgrind. What is valgrind going to tell us right now? Oops. There is a memory leak. How big is it? 80 bytes. I wonder why. 80 bytes. What are we leaking? This original array here, how many bytes did it take? 10 times 40. Oh, so 4. So that's 40, right? That doesn't account for 80 here. Well, am I freeing the second one either? Nope. So 40 plus 40, 80, right? And so there are 80 bytes that are definitely lost. Now, what if I restore this free right here? Free the first one because you're done with it, and now go ahead and create the second one. What should we expect here? Only 40 bytes is lost now, right? Right there. And then if we free that one before we exit, we'll see that no bytes are lost at all. There we go. Now, back to stewardship here. Who owns this memory? Let's go back up to the ones array here that creates the array and then tries to give it back. Am I done with it at this point? Could I go ahead and free up the array right here? No. Why? I mean, it's like computing a value total and then throwing it away and not returning it at all. You often see that warning message that you get when you use the WAL flag, where you it reaches the end of a non-void function and you haven't returned anything. You computed some result and then you never gave it back. Right? You actually, in this case though, I created a result and then I'm destroying it. I'm deleting it. I'm freeing it up. Right? You don't want to do that. Let's find out what happens when I do though. Save it. 11 errors. Why? Because get one's array, it was destroyed before you gave it back. Right? And so when we tried to access it down here, I wonder what would even happen if I tried to print it out. Yep, we freed it twice. Right? Because it got freed in the function, and then it got freed here. We got away with it a little bit, because we got away with a little bit of the printing. But it ultimately, at the end of the day, it detected that we freed it twice. We freed it here, and then we freed it again down here. All right? So this function does not own the memory. It creates the memory, right? And this is a resource that now somebody needs to take care of. But it gives it back to the calling function, the main, and now ownership transfers to the main, and the main is now responsible for cleaning it up. Right? So this is wrong. I'll go ahead and make sure that this is all in the notes here. There we go. All right. So that you can see some examples here. So again, using arrays with functions. Passing an array to a function, you have to tell it how big it is. All arrays are actually memory addresses. So you simply define it to be a pointer, because it's a pointer to not just one element, but multiple elements, 5 elements. To pass an array to a function, you pass it as a pointer. So if it's already a pointer, you don't use the star, you don't use the ampersand, it's already a pointer. In other words, you pass it by reference. And again, the example that we looked at here was to compute the sum of elements in an integer array. Right? And also, the other observations that we made along the way. That when you pass an array to a function, you also have to pass its size, because that is bookkeeping. There is no way in C for you to determine the size of an array. Every piece of code that uses the array has to be told how big it is. Int star could be a single integer, as you've already observed in your last 2 hacks, or it can be multiple elements. The way that arrays actually work is by using pointers and pointer arithmetic. And for that, let me go ahead and, just a second, let me pull up the figure here. I made a new figure, and we'll introduce it into the book eventually here. My book, not the Xi books. But here's the way that you should think about it. That's too big. Zoomed in out too much. There we go. Here's the way that you should actually think about an array. When I go arrays of 0, the 0, the 1, the 2, those are all indices. They're actually a memory offset. ARR is a memory address. So to get to the first element, you jump to that memory address with an offset of 0 times however many bytes an integer takes, which of course is the array plus 0, pointing to the first element in the array. When you go to the second element, the element at index 1, that's basically equivalent to saying ARR, the memory address, plus 1 times however many bytes an integer takes. In other words, this memory address plus 4 bytes over. And that is going to end up pointing to the second element, 3 here in this case. Likewise, arrays of 2, 3, oops, then there's a typo here, sorry about that. It's just a memory offset. 2 times number of bytes away from array. In other words, just add 8, right? And so each one of these jumps here, jumping from this memory address to this memory address to this memory address, 4 bytes, 4 bytes, 4 bytes, 4 bytes. And you're simply multiplying an offset from the original memory address. That's how memory works. And that's why we have 0 indexing instead of the natural way of thinking about it, which we always start counting at 1, 2, 3, 4, 5, right? A computer doesn't do that, and this is why a computer doesn't do it. It's because it's all memory offsets. Question?
So whenever you're instantiating a dynamic array, is the malloc working the same way by like basically what's happening is creating a bunch of blocks?
It doesn't create one block, it creates only one block. So if you want 1,000 integers, then it says, okay, you want 4,000 bytes. Here's an entire block of 4,000 bytes, and here's the pointer to the beginning of it. And then when you do the typecast on the other end, you're saying, okay, now break it up into 4-byte chunks, right? And so that I can have the first integer, the second integer, the third integer. That's why when you have a double array and you do the typecast, you're essentially breaking it up into 8-byte chunks, 8-byte chunks. Right? Get that out fast. Right? Okay? Okay, need to come back over here. There we go. All right. You can also return arrays from a function, right? And that's what we just did with the ones array. Oops, I wanted to do it like this. There we go. The return type is simply a pointer, int star arr. You don't want to return. You don't return the size because you can't return 2 things. Let me go back to our example here. Did I design this function to also return not only the array but also the size of the array? Well, first of all, can I return 2 things from a function? No. So how could I do that? Do I need to do that in this case? No. Why? You're the one that told me. You told me you wanted an array of size n, right? Of course you know how big of an array it should be. Right? But there are situations in which you create an array and then you give me back a new array, give me back that array, and also you have to tell me how big it was, because I don't know exactly how big it was. So let's go ahead and do an example of something that looks like that. All right, I'm going to go ahead and write out the documentation first. So what we're going to do is this function takes an array of integers and returns a new array containing all of the positive values in the array. Ooh, cool. So you gave me an array of, say, I did put this in the notes, so I'm going to go ahead and get rid of this. I'm going to go ahead and go with a static array now. Just ignore that declaration. But say 2, -5, -4, 5, 7, -2, -1, 0, and 4. There we go. How many things did I put in there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Right. So I've got an array of size 9. What I want to do is I want to filter that. I only want the positive values. 2, 5, 7, 4. What about 0? Is 0 positive? No. Is 0 negative? No. Neither. But is 0 even or odd? Or neither? Careful, it is odd. Or it is even. Right? It is even. It is not neither. Right? So there's your double negative for the day. Right? Only the positive values in the array. So for example, for this particular test case, it should return 2, 5, 7, and 4. In other words, it should return an array of size 4. How do I know how big it's going to be? If I give you the array and you filter it out and you only create a new array with those 4 elements, you have to tell me how big it is too. Because if I know how big it was, I did all the work. Right? So let's go ahead and design that function here. All right, so obviously we'll be returning a new array here, so int star, and I'll call it get positives. Right? Now, what do we need to take as input here? We need to take the original array, right? Array. What else do we need to take? Always the size of the array. Anytime you see int star ARR and you don't have this, implicitly you are passing a pointer to one integer. But anytime that you see an array along with int n or something similar, you know that you are passing in an array of size n. Right? Again, it's idiomatic. Right? It's just, that's the way it is. Right? Do I need to pass in anything else? Let's come back to that. So what I want to do is I want to implement this function and then come up with how big it should be. So I'm going to iterate through the array and find out how many integers are positives, ... All right, that's easy enough. I'll go ahead and create int numpos, right? Number of positives, and I will make sure that I initialize it to 0. If I don't initialize it to 0, how many positive values are there right now? Don't know. Dead beef, right? Garbage. So, another idiomatic for loop for int I equals 0, I is less than n, I plus plus. If the array sub I is positive, so if it's greater than 0, then I will say numpos plus plus. Again, I'm just counting up the number of positive values in here, okay? I haven't actually created my array yet. So let's do that now. Now that I know how many positives there are, say 4 in the example from the main, I can create a new array. Can I call it ARR? Nope. It's already taken. So a joke one would be BR, right? Because A, B, C, right? Her, and there are arrays, but ARR is short for array. BR is not short for beret, right? So you could call it result maybe. Okay. And let's go ahead and call malloc, right? And it'll be numpos. Will it be n times size of int? N is the size of the original array. How big should my new array be? Only big enough to hold however many positives there were. Right? Ultimately, I want to return that value too, result. Okay? Now, I have created, I went through and counted up the number of positives, 4. I created a new array of size 4. Are the positives in that array yet? Nope. So let's go ahead and iterate over those values again. And if it's positive, then we need to put the ith value into the result, ... How do we go about doing that? Results of I is equal to array sub I? Yeah, okay, help me out. What's going on here?
If you do it that way, you go past the bounds of the result array, so you have to have a specific variable.
I'm going to have another counter variable, another index variable here, right? Because let's think about iterating over this value, right? The first one will work. That will be at index 0 and index 0 in both arrays. The second one, though, we don't copy that over. So as I'm iterating over the original array, I is incrementing forward and forward and forward. But if I put, say, the last one here, which is at index 8, if I put that into the result of 8 when it's only of size 4, I've gone beyond the size of the array. So what we're going to need is another index variable. Well, I've used I. What could I use? What else could I use? J. Or index of result. I'll start it out at 0. I'll go ahead and use that. Index of result. I, J, K are perfectly fine stylistically, but you start to lose the forest for the trees, right? Which one was I was for the first one, J was for the second one, K was for the third one. That should be pretty straightforward, but if you use something like this, index of result on result, absolutely clear. A little bit more typing, but absolutely clear. Am I done? Is that it? Am I changing index of result ever? Nope. I'll advance increment index of a result. So to the next value, right? So how do I increment it? Plus plus. There we go. Okay, great. Let's come down here and try to use this thing. What was it called again? Get positives. There we go. How do I call it? So int, here I'll call it BRR, right? Get positives. I'll pass in ARR and N. And remember, we were thinking anything else? I don't know. We'll come back to it in a second here. Now I want to iterate over the BRR to print them. So another idiomatic for loop here. For int I equals 0, I is less than something, I plus plus, and I'll print f BRR sub %d is equal to %d and the line. We're going to print I, and we're going to print whatever is in BRR sub I. Now, here's where my question comes in. How big is BRR? 4 in this case, right? That would certainly work. Let's go ahead and see it in action. Oops. What's wrong? Oh, okay. Still have my question marks there. I'll get rid of them for a second here. There we go. All right. So it should print out what again? 2, 5, 7, and 4. 2, 5, 7, 4. That works. But it required me to know what? It required me to go through that array and count up, oh, it's going to be of size 4. Should I be doing the work in that main? That's duplicating effort, right? The function is responsible for creating a new array with the positive integers in it. It's responsible for counting up the number of positives. It's responsible for creating that array and populating it. Why should I also have to duplicate that amount of work? Okay? So what I want is, I want the size of BRR, How do I get that? Could I ask get positives to give me two things? Both the array and the size of the array? Nope, that doesn't work. So, ideas. Is there a way that I can return multiple values? Yeah. A pointer. A pass-by reference variable. Right? Int. Size of burr. Now, size of result. I should call it what it is. Right? Size of the result. Now, is this a pass-by reference variable? Nope. It is a pass-by value variable. I'm giving the function the value. If on the other hand, I change this to star, to a pointer, now it's a bucket that I'm giving it. It's going to fill that bucket with the size of the result. How would it do that? Num positives. So, size of the result is equal to num positives. Is that correct? Careful. Size of the result is a pointer. Num positives is a integer. So we've got a pointer on the left-hand side, a regular old variable on the right-hand side. What do we do to that pointer to make it into a regular old variable? Star, just like you're doing in your hack this week and in your lab last week. Okay? Now down here, I need the size of it. So int size of burr, right? And I need to pass that now as my third variable. Is that how we pass a pointer? Remember, it expects a pointer, and this is an integer variable. So how do I pass this? Is it star? Nope. Is it just like it is? Nope. So by process of elimination, it must be ampersand. All right? And it works as before, but also, if I add 1, 2, 3, right? Now it should be of size, what was it before, 7? There. Oops. Oh, what's wrong? I saved you, didn't I?
You have the size of burr right.
Oh, where? I have size of burr right here. Size of burr, size of result, and we return it. Come on. Why are you dying? All right. the demo. Come on. Size of result. Get positives. I'm wondering what's going on here. Num pause.
Did you ever set size of query to size of result?
Well, it's being passed by reference here, so and yes, I did right here. Size of result. It's called size of result right here. All right. I don't know if we should spend more time on this or if I should fire up a GDB. All right. I'll give you a preview of what we're going to do very, very soon. All right, GCC. I'm going to give it a new flag. This new flag stands for the GNU debugger, or GDB. All right? GDB is GNU debugger, right? And demo. All right? It seems like it doesn't change anything. But what it does is it retains all of the function names, all of the variable names. Normally, function names and variable names, they get thrown out the window because ultimately it's a machine code and it doesn't care about any of that stuff. But what I can do now is I can run this through a tool called GDB, which is basically another dynamic analysis tool, but it's called a debugger. A.out. All right. And now I'm in an interactive debugger right here. What I can do is I can run my program, right? And it'll run the program. Now, of course, there's an error here. We need to understand what's going on here. Why is this failing us? So what I'm going to do is I'm going to set what's called a breakpoint. And I want to find out what's going on inside get positives here. Get positives. I'm going to break in get positives. And then I'm going to run it. There we go. It stopped the program. It stopped the program at line 37. And it's telling me that here we are. Right? The program is still running. It's just paused. And what I'm going to do is I'm going to go ahead and go with layout next here so that I can actually see what's going on in the program. And unfortunately, I don't have too much real estate here. So what I want to do now is I want to step through my program. To do that, I want to go to the next line. And it goes to the next line. Next line, num positives. And I can also look and see what the variable values are. For example, I can say print, what was it called? Size of result. And it's an integer pointer. So this is a memory address. If I want to, I can go ahead and dereference that, size of result, and see what's stored in there. Right now it's 0. Okay? I'm going to be looking for that to be updated to 7 or whatever. Right? And I've got my for loop now, so I can print, n, and see that it's going to run for 9 iterations. So next. Sometimes the highlighting gets screwed up here, so you can also always refresh. There we go. All right. And now we're on num positive. I can print the entire array. Again, it is an integer. It's an integer pointer, so it's pointing to an array. That's perfectly fine. What you can do is you could go print. I think it's array, and then there are 9 elements in it. Print array, and there are 9 elements in it. There we go. 2 negative. That's what we passed in, right? Ooh. That's not what we passed in, right? That's not what we expected. Oh, now I realize what we did wrong. Right? I'm glad that I went through this exercise, though. But anyway, we'll look at another example later on when we get to formal debugging. But if you want to, you can start using this as a tool. Instead of typing next and going line by line, you can just go ahead and go n. And I believe you can go enter to enter the last command you gave it, so that you can iterate through all this stuff and see that, okay, num positives, print I, right? I is now 8, so we're about to break out of that for loop, right? Next, and now we're at this line 47, where we create that result, we set our index, print index of result, right? It's at 0, right? We started at 0, next, layout next, or refresh. You can only look at a few lines of code here at a time because, again, I don't have much real estate up there. But if you've got a nice setup, 2 monitors is the standard nowadays, right? Everybody's got 2 monitors. And then the lucky of us have 3 monitors, right? Now, I've got 4 USB-C ports, so as long as I'm running power through one of them, I can have 5 monitors, right? But then it starts grinding to a halt, so because it's just a Mac laptop, right? But anyway, next, right? You can, and then if you want to, you can continue the program entirely. So continue, right? And it'll run all the way to the end, okay? And then, of course, it needs to be refreshed. There we go. And it's done. It exited normally. So to quit out of GDB, you type quit. And I realized my mistake as we were walking through it, right? Sometimes it's called rubber duck debugging, right? If you just walk through it and go line by line, you start to realize, oh yeah, of course, that was it. So what was it? Originally, how big is this array? It was 9 elements, and then I added 3 more. But my bookkeeping, how was I keeping track of the size of this array? N. That needs to be updated to 12. All right. Save that. Oops. GCC. Run it again. And now you'll see that 1, 2, 3 are included. Okay? So that was a little bit of a preview of what's coming next. I'll go ahead and put this into the notes so that you have an example. All right. There we go. There we go. All right. So again, let's see, notes. There we go. All right. That's a way that you can have a function create an array and also communicate back how big the array that it created was. Okay. All right. One more thing before we go. So other issues. Right? So the first one will be multi-dimensional arrays. So we live in the 3rd dimension, right? Where we've got x, y, and z axes, right? We're 3-dimensional beings. A regular old array is a 1D array. Why? Because it's kind of like the number line, the x-axis. You have elements, and it's 1-dimensional, right? You can have a 2D array with both rows and columns. There we go. If you've had any linear algebra before, what do you call these things? Matrices, i.e. matrices, or those of us without linear algebra, what would we call that? If you've got rows and you've got tables. I just gave it a... If you've got rows and you've got columns, then you've got tables, right? There we go. You can also have 3D arrays. 3D, 4D, etc. arrays are possible, but not recommended. We are going to stick with 2D arrays, all right? In C, a regular old array is int star, right? So consequently, to have a 2D array, or a table or a matrix, whatever you want to call it, you use int star star. And I'll just call it MAT for matrix for short. Right? So what's the only difference? 1 star, right? So 1 star is 1-dimensional, 2 stars is 2-dimensionals, right? How do you think that you would get 3-dimensional arrays? 3 stars, how did you think you'd get 4-dimensional arrays? 4 stars, et cetera, et cetera, et cetera. Again, don't go that far. If you find yourself ever thinking, I need a 3-dimensional array for some reason, rethink what you're doing. There's probably a better way of doing it using structures or objects or something like that. 2D arrays are pretty much the maximum, right? To index a 2D array, you provide both the row number and the column number. So for example, if I go array ARRs of 3 and 4, right, is the 4th row, 5th column. Right? You can think of it differently if you want to, but this is the usual way of thinking about it. It's called row major form, where the first coordinate, 3, that refers to the row. And why do we say that it's the fourth row? Because it starts at 0. 0, 1, 2, 3 is the fourth row. 0, 1, 2, 3. Now the fifth column is going to be 0, 1, 2, 3, 4. Right? And that's the second component there. Okay? So what I want to do is I want to come over here to my visualization tool and edit this code. And let's go ahead and see what that looks like to create, say, a 3 by 4 matrix. Right? First of all, get rid of all this stuff. Right? So let's go ahead and create a 3 by 4, we can go 5 if you want to, table or matrix. Right? Or just call it 2D array. Right? If you don't want to use one of those other terms. That's what we'll use anyway. Right? So to create that, first of all, I'm going to need to keep track of the number of rows and the number of columns. So if n is going to be used for the number of rows, what should I use for the number of columns? I could use numcols and numrows, or m. Okay, why? Because it's the next one. Right? By the way, we won't get into it at all, but C++ is an object-oriented programming language that came along about 10 years after C. Why do you think they called it plus plus? If I've got an array, if I've got I and I want to increment it, what is it? Gives me the next I. So C++ is nothing more than a little joke. You might have heard of a programming language called C#. Why'd they call it C#? Music, folks. If you've got a C, what's the next note above it? C#. Haha. Right. Clever. Clever and stupid. All right, so for int I equals 0, I is less than n, I plus plus. Actually, what I need to do first is I need to create an array of pointers to point to each row. Right? And we'll see this in the visualization when I actually execute this. So to create a matrix, or I'll just call it, I can't call it M because I've already used that. I'll call it T for table, or don't get cheap and write it out the entire thing, table. I'm going to have to call malloc. All right? Now, I need 3 pointers. I need a pointer to point to the first row, I need a pointer to point to the second row, and I need a pointer to point to the third row. So I'm going to need 3 rows. How big is each pointer that's going to point to each row? So size of int. Is int a pointer? Nope, that's a regular old integer. So how do I get the size of a pointer, of an integer pointer? Int star. And I want 3 of them. And when I do my typecasting, it has to match the left-hand side. So int star star. Oops. There we go. Now what I need to do is I need to iterate over, and I need to create that entire row. So here are my 3 rows. That first row is going to have to be 5 integers. The second row is going to have to be 5 integers. Okay? So I'm going to have to call malloc for each row. Malloc on the first row, malloc on the second row, malloc on the third row. And it'll be table of I is equal to, here it is going to be int star. It's just a regular old call to malloc that we're already familiar with. And it'll be 5 times size of, and here they are going to be integers. I want 5 integers. How many bytes does each integer take? Size of int. Now let's make sure that we are using these variables here. So I'm going to come back here and change this to n. I'm going to change this to m. All right. We do have a question online here. Could you extend the reading deadline? Oh, okay. I'll look at that line later. All right, there we go. All right. So that sets up memory. Now what's in that table right now? It's a 3 by 5 table. If I were to print it out, what would be in there? Don't know. Garbage. Who knows? Right? So how do I iterate over it to set values? And I'll just have a counter variable here. Set values in the table. Int value is equal. I'll start it at 10 and then I'll go up by 10 or something like that. Right? I need to iterate over the table and set each one of those values. So in other words, for each row, ... I need to iterate over the column. For the first row, I want to set 10, 20, 30, 40, 50. Then go on to the next row. 60, 70, 80, 90, 100. Next row. where did I leave off? 110, 120, 130, 140, 150. Right? I will need what? Another nested for loop. For int j equals 0. J is less than m for the number of columns, j++. And I will set table sub I, j equal to value. And then I'll go up by value plus equals 10. There we go. So I'll go 10, 20, 30, 40, 50, etc. Now, I'm not going to print this out because we can actually visualize this execution. Okay? Hopefully it doesn't take too long. C# is also meant to be a joke because, yep, okay. We are on a 10-second, 20-second delay for some people. So, yes. All right. All right, so here we've got the table, M and N and the table. I'll go ahead and jump to 5. All right. You know what? Let me go ahead and zoom out here so we can actually see it. So that table is going to end up pointing to an array of pointers. There are 3 pointers. Each one of those pointers is going to point to that row, the first row, the second row, and the third row. At least the way that I've done it here. There are alternatives I'll mention. And if you're interested in those alternatives, go ahead and watch the pre-prepared videos and or read the my book, not Zai books. Right? But anyway, we go into this loop here. We initialize that first row. The next loop is going to initialize that second row. The third loop is going to initialize that third row. And again, as I asked when we were doing the code, what's in there right now? Well, who knows? Dead beef, garbage values. In this visualization, they're using a question mark because, again, it's uninitialized memory. Who knows? Right? Now, as we go through this, we're going to go for 0, 0. That's the top leftmost element, 0, 0. And we set that equal to 10. Then we're going to the next column and set that to 20, 30, 40, and 50. And that will end the inner for loop. Now we go back up to the outer for loop that increments to I is now 1. In other words, we're operating on the second row here. And it will go through again and set it equal to 60, 70, 80, 90, and 100. The third iteration increments I to 2. And now you're dealing with the third row and setting it equal to each one of those. Right? So, double pointer. You generally need nested for loops to do something like this. At least that's the clean way of doing it. And you can have 2-dimensional arrays. You can have 2-dimensional static arrays, but I already mentioned that static arrays are kind of bad because they're extremely limited. There we go. So that's now in your notes as well. Okay. Maybe one last thing, or at least I'll motivate the one last thing, and then we'll pick it up there next time. Constant array, or protecting arrays. If you pass an array to a function, that function can change the contents. Why? So we started this entire thing with pointers. Well, we started a couple modules back with pointers. We started with a demonstration of our first attempt at a swap function, where I gave you that function a and b, and I wanted it to swap a and b, 10 and 20. Did it work? Not initially, because we were passing them by values. The values got swapped, but what about the original variables? No. So what we did was we updated those to be passed by reference variables, so that the swap would be realized in the original function. How are we passing arrays in functions? Let's come back over here and look. How am I passing this array? By reference. Consequently, get positives could make changes to the array. Let's suppose that it did. Let's suppose that in addition to copying it over, we also set it to some random value. Array sub I, we'll set that equal to 42. Right? What will that end up doing with the original array? 42, 42, 42, 42, 42. Right? Do we want to allow that? Probably not. If I gave you an array I said, I want you to operate and like sum the elements up. Am I going to expect that you're also going to change the elements in addition to summing them up? No. So how can we protect against something like this? Yeah, we have enough time. Let's go ahead and introduce a new keyword here, const. So you might have seen const before. You probably definitely saw it from Xi books. What is it short for? Constant. Ooh, we saved 3 characters, A and T, right? Const. What does it mean? What does constant mean? Yeah, it stays the same. It's unchanged. By labeling this pointer here a const, it means it's unchanged. We're making a promise, right? We're solemnly swearing that we are not going to change this array. But you did, right? You set it equal to 42 on every single one. Let's try to compile this now. And the compiler will say, no, you can't do that. You said that it was const. It's read only. You're not allowed to make changes to it, but you did. You made changes to it on line 56 right here. Right? And so therefore, I'm going to refuse to compile. It is actually an error. It's not a warning. Right? So if you're not going to make changes to an array, you should use the const keyword, right, to make that promise. Right? Often, we will want to prevent changes to an array. You can use the const keyword to indicate that you will not make changes. If you use const and do make changes, the compiler will issue an error, and you won't be able to compile. Right? It's best practice to do this even if you're not going to make changes, just make it const, period. Right? If you are going to make changes, can you make it const? Nope, because if you do need to make changes, like here's an array, add 1 to everything in it, right? You are actually asking the function to make changes for you. And if you want changes, then you can't make it const, right? So that was easy enough to get through. Anything else? I think we've got a couple of more things to talk about. Yeah, shallow versus deep copies, and but otherwise, we'll finish up with arrays on Wednesday. Okay? No questions? All right. No questions online. All right. I will see you on Wednesday then.